All right, welcome ladies and gentlemen. This is video number 2 for nuclear chemistry. You're going to need your notes open to where it has the video number 2 section. And I don't think you're going to need your reference table for this one. In this video, we're going to be talking about artificial transmutation, energy associated with nuclear reactions, and the difference between something called fission and something called fusion. So in the last video, we talked about natural transmutation, where a nuclei, an unstable nucleus, will spontaneously decay and change, because transmutation change, right, into something else. Well, artificial transmutation now, what is that? First of all, it has to do with a stable nucleus. A stable nucleus will not spontaneously emit a particle because it's, stable. However, you can force it to decay. It can be made to decay by colliding it with high energy particles. And when you collide it, when you're basically throwing these super high energy particles at it, that's called bombarding it. And if you just keep on throwing these super high energy particles at it, essentially you make it unstable, and then it will emit some kind of radiation and turn into something else. So artificial transmutation, it's a change, right? We're changing the nuclei, the nucleus. That occurs by taking something that's stable on its own and throwing other high-speed particles at it, bombarding it with these other particles. So, for example, this is an example of artificial transmutation, because this is our stable nucleus, this nitrogen 14, and then this is the alpha particle that we are bombarding it with. And that process of basically throwing this alpha particle at nitrogen 14 causes it to now change into something else. It now changes into oxygen 17, and then we also have this additional proton that's left over. So this nitrogen 14 does not spontaneously turn into oxygen 17, but if you keep on annoying it and hitting it up with these alpha particles, then eventually, yeah, it's going to change. So this is called artificial transmutation, because it's not happening on its own. Where does this occur? Where do we see artificial transmutation? Particle accelerators. Particle accelerators are all examples of artificial transmutation. Cyclotrons or synchrotrons, where they use magnetic or electrostatic fields to basically speed up small particles, like the alpha particles or the protons, and then they put the nuclei that they want to bombard it, the particle with, in location, and then they wind up shooting these really, really high speed particles at it. The pictures that you see here, these are from CERN, which is in Switzerland, and it's the largest particle accelerator in the world. The one that's right here, if you notice this very large track, this is the Large Hadron Collider. And that is actually a 17-mile long particle accelerator, so it's hugely long, but it can get the particles up to a very, very high speed. So why would we want to do this? Why do we want particle accelerators? Why do we want to bombard nuclei with these high-speed particles and get them to change into something else? Because the process of doing that releases a tremendous amount of energy. Any nuclear reaction, and this is a huge point, will involve energies that are millions of times greater than any ordinary chemical reaction. You get way more energy from a nuclear reaction than you do even combustion, which is one of the most exothermic chemical reactions that exist. But combustion does not hold a candle, pun intended, to any sort of nuclear reaction. You get so much more energy. And if you think about this is something you already know. If you think about the amount of energy that you get from something like an atomic bomb, which involves the changing of nuclei into something else, right? They're far more destructive than just a simple fire. So we have tons of energy that comes from nuclear reactions. Now, why does that energy coming from nuclear reactions? Because of something we've actually seen before. I hope you're enjoying the picture of Einstein right there, by the way. Nuclear reactions convert a small amount of mass into energy. So nuclear reactions we call that mass defect. They lose a tiny bit of mass in the process of changing the nucleus, and that mass goes into Einstein's famous equation right here is to m gets multiplied by the speed of light squared, and we get energy out. And we get just tons of energy out. So this is why you'd want to do artificial transmutation, because of the benefit of getting lots of energy. Fission and fusion are two types of nuclear reactions that can also generate this huge amount of energy. And we're going to talk about them because their names kind of sound similar, but they're actually very different. So fusion, first up, fusion. To fuse, right? To fuse means to combine. So the word fusion must be about this combination, and it is. So it's combining two things together. So it's a combining of nuclei together, actually. And we see fusion. This can only happen with very small nuclei. So we're talking hydrogen, helium, and that's about it. Like possibly lithium, but as soon as you get any bigger than that, then it is no longer fusion. It would be artificial transmutation instead. So fusion is tiny nuclei, or small nuclei combining to generate something bigger. So if you notice at this picture at the bottom, we have an initial atom and then a second atom, like two different nuclei, deuterium and tritium, which are, like it says here, isotopes of hydrogen. So they're both hydrogen. This is those are our two isotopes of hydrogen right there. And then fusion, notice they have combined. And we get something that is larger out of it, right? We get helium out of it and a neutron right there. And lots and lots and lots of energy. So this production of energy from this nuclear reaction. Fusion occurs in the sun and it occurs in stars. And helium was actually first discovered in the sun. It was thought for a long time that helium actually didn't exist on the planet Earth because no one could find it. It obviously didn't react with other elements. It was obviously very stable. And it was first found because they're like, oh, there's this element in the sun that we just haven't found anywhere on Earth. And so that's where, like helium, the reason that we're seeing helium in the sun is because it was fusing together. It was the product of the fusion of hydrogen isotopes. You need a ton of heat, you need a ton of pressure in order to get fusion. Fission, on the other hand, is very much the opposite of that, whereas fusion is to combine, to bring together. If you think about fission, or in earth science, like a fissure, F-I-S-S-U-R-E, which the roots are related, it means to split. So fission is the splitting of atoms rather than the fusing or the combining of atoms. And fission involves literally the exact opposite type of atoms. Instead of very, very small, now we have huge atoms. They're very large. They're unstable nuclei. You bombard them with neutrons, and they will split apart and generate tons of energy in the process. This is why you'd want to do that. So the atoms that are involved, we've got uranium, we've got plutonium, we've got neptunium. These are the real big guys off of the periodic table, the big, big atoms. This example right here, notice that we are bombarding a neutron at the large atom, and we cause it to split into these smaller atoms, right? So this is big, and these guys are smaller. But it's also giving off additional neutrons, and that goes to this point right here where fission propagates, meaning if you just start a fission reaction, it will keep itself going, i.e. it will be a chain reaction, because like this neutron that's right here that came off, this can then split another atom, and it sort of keeps on going. Where do we see nuclear fission? Nuclear power plants are using nuclear fission. That's what they're doing. They use fission to create lots and lots of energy. Also weaponry, right? That uses nuclear fission. So fission, very large atoms that are being split. Fusion, very small atoms that are being combined.